Welcome to lecture number 8 for ECE 320, Digital Electronics. Today we're going to talk about AC to DC converters. Now, the whole point behind AC to DC converters is to convert 60 Hz AC to DC. And you might wonder, why are we using AC? Well, Electroboom's actually got a really good video on that. If you go under electronics and lecture number 2, AC versus DC, Electroboom discusses Edison versus Tesla, the fight they had back in the 1900s, why Edison wanted to use DC, Tesla wanted to use AC. Basically, the power grid doesn't work at DC. It's got to be AC. However, almost all the components that you have in your house are DC, so you need an AC to DC converter. Another good one to watch is the Full Bridge Rectifier by Electroboom. Basically, Electroboom's got really good videos, so I'd recommend watching that. Otherwise, you're kind of stuck with me. So anyway, the purpose of an AC to DC converter is to convert 60 Hz AC to DC. AC is much more efficient for power grids. That's kind of why we have an AC power grid. Basically, transformers don't work at DC. And what happens is, if I want to transfer, say, a megawatt of power long distance at DC, if I have 120 volts at a megawatt, I need 10,000 amps. The transmission line losses are I squared R, so 10,000 squared is a huge number. Even a very small resistance is going to result in a huge loss in the transmission line. What transformers do is I can take the voltage and bump it up by 1,000 times. So rather than transmitting 120 volts, I can transmit 120,000 volts. Power has to balance, so if the voltage goes up by 1,000 times, the current goes down by 1,000 times. And then the I squared R losses go down by 1,000 squared, or a million times. So it's much more efficient to transmit high voltages than low voltages. But if you hit your house with 120,000 volts, it'll probably burn down. So the transformers in the city take the 120,000 volts and bump it back down to 120 volts so your house doesn't burn down. That only works at AC. Most electronic components, however, are DC, like your computer, anything with a diode, flashlight, LED, transistor. Those are typically DC devices. If I powered my computer with AC, it would turn on and off 60 times a second. And if you know how long it takes your computer to boot, rebooting 60 times a second just doesn't work. So you've got to convert back to DC to power your components. That's today's lecture. The heart of an AC to DC converter is a rectifier. And there are two types, the half-wave rectifier and the full-wave rectifier. Now this is what the half-wave rectifier looks like. I take a load, say 100 ohm resistor, and add a diode in series. What that does is have an AC source, say 20 volts at 60 Hz. Oh, kind of a sidelight. If you're going to do something like this in the lab, don't use the 120 volts straight out of the wall outlet. That's got a little bit of power to it. That can hurt you. Use a wall transformer. We've got some of those in the lab. Just a little, 20 volt wall transformer. You plug it into the wall. It's rated at 12 volts. That's 12 volts RMS. And if you look on the oscilloscope, it's actually 20 volt peak. Plug that into the wall. And what those look like are kind of these guys, just the wall plugs. They're both DC and AC. The AC's got a small transformer in it, drops the 120 volts down to 20 volts. And you need like 20 volts peak, 12 volts RMS, and maybe 500 milliamps for the stuff in this lecture to work. You can also get DC power supplies. This has the AC to DC converter already built in, which is fine for user standpoint, but in terms of electronics, we want to see how those work. So again, use a wall plug to bring this down to something reasonable, like 20 volts peak, and have that power your device. So anyway, back to the ranch. A diode acts as a valve. So what happens is when I have a positive voltage, the diode turns on and I lose a 0.7 volt drop across it. So the red line follows the blue line, minus 0.7. When the voltage goes to negative, I try to push current backwards. Then the diode turns off. When it's turned off, V1 is just ground. So that's what you get at V1. And you can see that in Circuit Lab. If I build this in Circuit Lab, you just take an AC source. If I use two resistors and a ground, connect all these up. Change this to be 20 volts at 60 hertz. Then let's look at the voltage right here. Let's look at both voltages. Here's your V1, here's V2. 60 hertz has a period of 16 milliseconds. So when I simulate it, let's bring this up so you can see what I'm doing. I'm going to go under Simulate. Now I need to do time domain. Since this is a sine wave, assigning a number to it doesn't really work too well. I'd rather like to see what the shape looks like. The period is 16 milliseconds, so let's simulate it for 50 milliseconds, about 3 periods. Make the time step 50 microseconds, gives me 1,000 points on the plot. And let's look at V1 and V2. So when I run that, this is just a voltage divider. V2 is just half of V1. And I get both positive and negative. That's a resistor. Now let's go back and replace R1 with a diode. And let's make that a 4004 diode, similar to the ones we have in lab. Now what happens is when the voltage is positive, the diode turns on, and V2 equals V1 minus 0.7-ish. When the voltage goes negative, the diode turns off, and V2 is 0. So now when I simulate it, that's what I get. Okay, when the voltage is positive, V2 follows V1 down by 0.7. When it goes negative, the diode turns off. So that's kind of the heart of a half-wave rectifier, just a diode. A full-wave rectifier is a little bit fancier. I use 4 diodes. So kind of what happens is when the voltage is positive, current's going this way, diode 1 turns on, and current goes up, goes down, comes back, then diode 4 turns on. So 1 and 4 turned on when the voltage is positive. When the voltage is negative, current goes backwards. In this case, diode 2 turns on, and diode 3 turns on. So you're kind of alternating 1 and 4, 2 and 3, 1 and 4, 2 and 3. The net result is that the load, the current's always going top down. So this looks like a full wave rectifier, or the absolute value, minus 1.4 volts, because at any given time I've got 2 diodes. So in Circuit Lab, this is kind of how you draw it. I put this in the middle just to avoid having the wires cross. I've got 4 diodes. At any given time, 2 diodes are turned on, 1 and 4, or 2 and 3. If I look at the voltage at V2, time domain simulation. Let's run it for 50 milliseconds again. Time step 1,000 times smaller, 50 microseconds. And let's look at V2. What we see is that this is your 20 volt peak sine wave minus 1.4 volts-ish. That's when 1 and 3 are turned on, then 2 and 4, 1 and 3, 2 and 4. And you kind of see that. If I disconnect one of these, like let's disconnect this guy. So I just have 1 and 4. This is a half-wave rectified sine wave. So again, this will be a 60 hertz sine wave at V2, or a 60 hertz signal at V2. That's my half. If I turn on the other two, I get the other half. The net result is the waveform at V2 is now 120 hertz. And the reason for that is you get the negative and positive. I get 2 humps per cycle. So in 3 cycles, I get 6 humps, double the frequency, 120 hertz. And I lose 1.4 volts. Kind of one sidelight is if you have a full wave rectifier, the source ground has to be floating or the load has to be floating. I can't ground them both. If I do ground them both, this is what happens. I try running it, and I expect to get a full wave rectifier. I don't. I get a half wave rectifier. And the reason is when I ground the source and the load, on this side of D4 I've got ground, on this side of D4 I've got ground. So D4 never turns on. Without D4, you have a half wave rectifier where I'm losing 1.4 volts, 2 diodes across it. So anyway, that's the full wave rectifier. The advantage is I have twice as many peaks, double the frequency. So it's actually easier to filter this out, keep the ripple, the noise down with the full wave rectifier. The disadvantage is I need 4 diodes rather than 1. And the source and the load can't have the same ground. One of them has to be floating. So, analysis. How to convert a half-wave rectifier into a DC signal. Now what I want to do is get a DC signal at V2. So let's take this guy. One way to do that is add a capacitor right here. And this is my load, so I'm going to pull them out way over here. I want to drive a 100 ohm resistor, let's just say, have a big hog-in capacitor at this point. So if I do something like make this 10 microfarads, what happens is initially when this turns on, I charge up the capacitor. When the voltage goes down, the diode turns off and the capacitor acts as a battery. It stores energy and drives the load. So here's kind of what happens. Going for 3 cycles. The capacitor charges up and then it discharges. Charges up and then discharges. This is what happens if the capacitor is too small. I don't have enough energy. Typically, you've got to have a really big capacitor, like 1,000 microfarads. If you have enough capacitance, this stores enough energy. And I charge up the capacitor, then it discharges. Then the diode turns on, charge up the capacitor, and it discharges. So what I wind up with is, on the orange line, I have a DC signal. There's an offset. If I zoom in on it, there's an average voltage right around here, about 18 volts looks like. And there's a ripple. It's 18 volts plus or minus. That gives me a DC term, the average, and the AC term, the ripple. Now what I want to do is both analysis and design, analyze the circuit to calculate the DC and AC voltage, or design a circuit for a specific DC and AC circuit, AC voltage. So this would be kind of the heart of an AC to DC converter. I need this capacitor that acts as a battery. It stores energy and powers the circuit. If I want to reduce the ripple, what I can do is add an inductor. In here. Inductors are kind of like a variable resistor. At DC, this is 0 ohms, so the DC voltage goes straight through. At AC, this is J omega L. If this is bigger than 100 ohms, say twice as big, so it's 60 hertz, I want 200 ohms. J omega L is 200. So that should be like 530 millihenries. If this is twice as big as R, the ripple should only be half as big. So now if I simulate it, and J omega L is 100, and that's at AC. By voltage division, it's half as big. And I've got my starting transient, then settle out. When I simulate, let's start at 50 milliseconds, trying to get out of the starting transient, and run it for another 50 milliseconds. And you can see the ripple is smaller now. That's what the inductor does for you. But at 60 hertz by voltage division, I got your R2 over J omega L1 plus R2 makes V2 smaller. If this is 100 ohms, the ripple will be roughly half as big. If that's still too big for you, what I can do is add a capacitor right here. And if this is 50 ohms at AC, well, at DC this is open circuit, has no effect at DC. At AC, if this is 50 ohms, half the resistance, the ripple will again be half as big. So picking C2 to be half of 50 ohms, so 1 over J omega C is 50. Did that wrong. So it should be 53 microfarads. We'll talk about this in a sec. This is 50 ohms at 60 hertz. Now when I simulate it, let's just look at V2. Now I've got a DC term, and an AC term, the AC is the peak-to-peak ripple. Peak-to-peak ripple is even smaller. So that's kind of the idea. I have a battery right here in C1, and L1 and C2 are filters, trying to reduce the AC ripple. So that's what we want to get to. So, given this circuit, find the voltage at V1, V2, both DC and AC. Now again, C1 is like a battery. It stores the energy when the diode turns off. L1 and C2 are filters that reduce the ripple. And R1, I don't want R1 to be in there, but all inductors have some resistance, so that's the resistance of the inductor that I just kind of have to live with. Now, the first step in DC analysis, find the DC voltage. Well, this is actually kind of hard. If you look at the voltage at V1, which I just erased, if I look at the voltage at V1 and V2, V1 is time varying. It's going to charge up to about 19.3 volts, then discharge, charge up to 19.3, then discharge. As V1 changes, then the current changes. So kind of have the chicken and the egg. I can't find the current till I find the voltage. I can't find the voltage till I find the current. So let's just do worst case. Worst case, I have a 0.7 volt drop across the diode. This is 20 volts peak, so V1 is 19.3 volts peak. That gives you the maximum current, or worst case. The current then at DC is your 19.3 divided by the total resistance, 130 ohms, gives you 148 milliamps. Now for a capacitor, I equals C dV dt. And this is a little bit confusing because the first capacitor is a battery. The second capacitor is a filter. They're both capacitors, but they serve different purposes. This stores energy and powers the circuit when the diode turns off. This shorts out the load at 60 hertz, reduces the ripple. So the net result is to know the signal at V1. It is DC voltage. Well, the ripple is 2.47 volts. The DC voltage will be the peak minus half the ripple. So it will be the 19.3 minus half of 2.47 volts, 18.06 volts on average. That's at V1. Now at V2, I have DC and AC. The DC voltage is take the DC voltage at V1, and by voltage division, 100 over 130 times that voltage, 13.89 volts. The AC voltage, well, this is actually kind of hard to do. if I look at the voltage at V1, it looks like this. That's not a sine wave. I know how to analyze circuits with sine wave inputs. I use phasors. I'm not really sure what to do with the triangle wave input. So what we're going to do is a typical engineering solution, change the problem, but change it in a way that you keep the flavor of the old problem. I'm going to keep the same DC signal, keep the same frequency, and pretend that V1 is a sine wave, 60 hertz, same peak-to-peak voltage. So I've got the same frequency, same voltage, same DC signal. It's almost the same waveform. It's not exactly the same, so the answers won't be exact, but it's close. Likewise, when we analyze the circuit in Circuit Lab, I'm going to have answers that are slightly different. If I want to analyze with this actual waveform, I can do it, but that's a much, much harder problem. That requires Fourier transforms that you cover in 343 signals, and we'll touch on it in this course. But for now, what we're going to do is change the problem, pretend that V1 is just a constant and a sine wave, keep the DC signal right here, keep the same peak-to-peak signal, 2.47 volts peak-to-peak, and the same frequency, 60 hertz, and analyze that. So, for AC analysis, making that approximation, V1 roughly is 2.47 volts peak-to-peak. The inductor, since I now know the frequency, 60 hertz, is J omega L, J188 ohms. Capacitor becomes minus J53 ohms. Put these two in parallel. And if you're using your trusty HP calculator, okay, come on, come over. It doesn't want to slide over. Slide over, you can do it. Hey, all right, did it. That was easy. Okay, I want to put these two in parallel. That'll be 100 ohms in parallel, minus J53 ohms. So 0, enter 53.05. So there's minus J53 ohms. Inverse. Add the inverses, take the inverse. Gives you 21.96 minus J41 ohms. Now we can use voltage division. It's your R1 over R1 plus R2 times Vn. So hit enter a couple times. There's your R1. R2 is 30 plus J188.5. So there's your R2. Add the two together. That's the denominator, R1 plus R2. Take the ratio. That percentage of 2.4744 volts. And I want to take the absolute value of that. Catalog, function, absolute. 0.743 volts. And the units, since V1 has units of peak to peak, that's the units of V2. This is 0.74 volts peak to peak. And that's your AC and DC voltages. The DC voltage is 13.8, so this is what V2 looks like. On average, it's 13.8 volts. And there's a ripple on it. The ripple is 0.74 volts peak to peak. And note, for AC, you got to watch your units. There's peak to peak, there's peak and RMS. They're all different. Peak to peak is twice the peak voltage. RMS is the peak divided by square root of 2. In the lab, if you measure this, on the multimeters you have a DC reading and an AC reading. The DC reading will give you the 13.89. That's your DC. The AC reading will give you this number, but it'll give you in units of RMS, which is the peak to peak divided by 2 square root of 2. So I can measure both of those in lab as well. Or in Circuit Lab, when you simulate it, the average, well, we'll talk about that in a sec. In Circuit Lab, I have my AC waveform. Take the maximum and the minimum. The average of the two is your DC voltage. The difference in the two is the AC voltage in units of peak to peak. So if I do that in Circuit Lab and check the answers, let's kind of do this. This is a slightly different circuit. But once you get the waveform, kind of move the cursor up here. There's the maximum, 19.15 for V1. And here's the minimum, 16.47. Take the average, that's your DC signal. Take the difference, that's your peak to peak. On the blue line, I want to get over till I'm at steady state. Here's the maximum, 18.07. Here's the minimum, 17.56. The average of the two is DC. Difference is AC. So comparing the two, the DC voltages match up at V1. The AC is a little bit different. At V2, the DC voltage matches up. The AC voltage is off a little bit more. Again, the reason the AC is off a little bit more is because I assumed that this waveform consists entirely of the first harmonic, 60 Hertz, nothing at the second, third, and fourth harmonic. That's not exactly true. So likewise, the answer isn't exactly right. It's close, but not quite. And what we're doing is a little bit conservative. The ripple's not quite as bad as I calculate. So we're kind of doing a little bit conservative, a little bit of worst case analysis. What that means is that the circuit's actually going to be better than I expect. If you want to find out how the circuit actually behaves, in my opinion, throw it in Circuit Lab. What you can also do is analyze using Fourier transforms, which we'll talk about later in this class. Way, way, way harder for slightly better answers. Typically, this is good enough. And if you want better answers, again, simulate it. That's what simulations are for. So that's analysis. And again, this is what it looks like in Circuit Lab. So take the peak and minimum. Difference is the AC voltage. There's your peak to peak. And the average is your DC voltage. Likewise at V2. So here's a handout. Given this circuit, find the voltage at V1 and V2, both DC and AC. If you pause the video, try to solve this, then we'll go over it. Okay, so picking up, to solve this circuit, again, this is about a 0.7 volt drop across the diode. V1 looks like this. The peak will be 19.3 volts. To find the current then, let's take 19.3 divided by the total resistance. 19.3 over 550 is 35.09 milliamps. From I equals C dV dt, I've got 35.09 milliamps. Sorry about my handwriting here. It's hard to write with the mouse. It's 1,000 microfarads times dV, and this is a half-wave rectifier. dt is 1/60th of a second. So solving, divide by 1,000 microfarads. Divide by 60th of a second gives you 0.548. That's the AC voltage at V1. The DC voltage then will be the peak 19.3 minus half of the ripple. So this distance right here is 0.548. Gives you 19.01 volts. On average, I expect that to be 19.01. So that's your DC voltage at V1. DC is 19.01 volts. AC is 548 millivolts. And the units are peak to peak. Now for V2, the DC voltage is by voltage division, 500 over 550. That times the DC voltage at V1 gives you 17.28 volts. That's your DC voltage. AC voltage. This is 60 hertz. So a capacitor at 60 hertz, or 377 radians per second, is minus J 265 ohms. The inductor, 2 henries becomes J 754 ohms. Put these two in parallel. 500 ohms. Let's bring you up. .500 ohms in parallel with minus J 265. Take that inverse, add the inverses. This is 109 minus J 206 ohms. Do voltage division. That divided by 50 plus J 754. So the real part's 50, complex part is 754. Those add, take the ratio, that percentage of 0.548. And take the magnitude, 0.225 volts. That's units peak to peak. That's your AC voltage. So that's analysis. Now, kind of a sidelight. One problem with AC to DC converters is the current are spikes. And what's happening is, in Circuit Lab, I've got my input waveform doing this. The output, let's do that in blue, kind of does the capacitor discharges, charges up, discharges, charges up, discharges. Only during this time right here is the diode turned on. That's when you're charging the capacitor. So the current looks like this. I get these spikes. That is a problem. LED lighting is way more efficient than incandescent lighting, but incandescent lighting is basically a resistor. If the voltage is a sine wave, the current's a sine wave. LED lighting is different. If I have an AC to DC converter for an LED light, that's a DC device, I'm going to get these spikes on the current line. And if you look at the current LEDs, and you look at the current going to them, I'm going to get these spikes. Now the problem is that spikes have high frequency components in them. If you have the current from a transformer has spikes on it, I'm going to produce losses, eddy current losses, hysteresis losses, the high frequency losses in the transformer. So I've reduced the efficiency of the overall system. I've just transferred the losses over to the transformer rather than my house with my light bulb. Another problem is if you have three-phase AC, kind of looks like this. If I have my phase A, phase B, phase C, these are three sine waves, each 120 degrees out of phase. Add them all together, the currents cancel. And you see that on the transmission lines out in the country. There's always 3 wires, and the 4th wire, the ground, is very, very small. In theory, I don't need a ground because all the currents will cancel. In practice, I won't have exact cancellation, so the current's almost zero, but not quite. That's for sine waves. If I have spikes for current, and I delay it, the currents no longer cancel. That's happened in skyscrapers. I replace all the lights with LED lights, and a skyscraper is basically a large city. I have 3-phase power going to the skyscraper. Phase A might go to the first couple floors, then phase B, phase C. They try to balance out the load. Replace the incandescent lights with LED lights, and suddenly I have huge currents on the neutral line, and it can burn out the neutral. What we really need is an AC to DC converter where the voltage to the LED, the load, is DC. The current from the utility is a sine wave. One way to do that is to have the AC drive an AC motor, drives a DC generator that drives the load. That works. But we're not about to have a generator motor combination for every light bulb. How do you do that in hardware? How do I have, in electronics, how do I take AC converted to DC, but keep it a sine wave from the utility standpoint, keep it a constant at the load standpoint? Do that with electronics at 90-95% efficiency. We currently don't know how to do that. If you figured that out, that's worth billions of dollars. But that's kind of a sidelight. With this circuit, I get spikes. And for small loads, that's okay. They've actually done studies at Otter Tail Power. If you have less than 30% of the lighting in the city's LED lighting, it's not a problem. There's enough inductance, enough capacitance to filter out those spikes. More than 30%, we're not sure. But anyway, that's a sidelight. So here's the challenge for you. Come up with a way to convert AC to DC at 90% efficiency so that the input is a sine wave, output's a constant. Figured that out, you're worth billions of dollars. But anyway, that's analysis. AC to DC design. Designers go the other way around. I know what V2 looks like. I want to drive a 100 ohm resistor. I want the ripple to be 100 millivolts peak to peak. Come up with C1, C2, L1, and R1 you're kind of stuck with, so that the ripple at V2 is only 100 millivolts. Well, first you pick your favorite rectifier. I'm going to use a half-wave rectifier. Full-wave rectifier gives you twice the frequency. You can use a smaller inductor, smaller capacitor, but I need 4 diodes. Second step, pick your inductor. The whole point behind the inductor is to reduce the ripple. So if this is 100 ohms, pick this to be so that J omega L is bigger than 100. So let's make it like 3 times as big. That'll reduce the ripple by 3 times. So if this is 100 ohms, this has to be 300 ohms. Or this becomes 795 millihenries. Doji doesn't sell 795 millihenry inductors, but they do have 1 Henry inductors. So let's make this 1 Henry. And from the data sheets, the inductor has some resistance. It's 50 ohms. So that's how I modeled the internal resistance of the inductor. I don't like it, but you're kind of stuck with it. Step 3. Find C1. So if this is 100 millivolts peak to peak, this has got to be bigger than that, but don't make it completely absurd. So let's make this 1 volt peak to peak. The inductor is going to reduce it by a factor of 3. The capacitor can reduce it the rest of the way. So let's make this 1 volt peak to peak. The max is 19.3 volts. At B1, here's what the waveform looks like. The peak is 19.3. The ripple, I just assumed that's 1 volt peak to peak. Take half the ripple, that's your DC level. The DC is 18.8 volts at B1. The current then is your B1 divided by the total resistance, 125 milliamps. That's your DC current. And then the ripple. I is C dV dt. 125 milliamps is C. I want 1 volt ripple. I want it to be 1/60th of a second. Half-wave rectifier. Solve for C. C is 2,000 microfarads. And that's pretty common. A lot of times you have really big capacitors in these AC to DC converters. That gives you C1. Now to find C2, first assume C2 equals 0 and find the ripple at V2. That'll be 100 over the total resistance times 1 volt peak to peak, 246 millivolts peak to peak. I want it to be 100 millivolts peak to peak, or 2.4 times smaller, so choose C to be 2.4 times smaller than RL. So this is 100 ohms, I want that to be 40 ohms. And actually it's going to be minus J 40 ohms, because that's a capacitor. 40 ohms is 1 over J omega C. I know omega, solve for C. C is 65 microfarads. And there's my design. I know C1, L, and C2. If I check in Circuit Lab, this is your V1. It's supposed to be 100 millivolts peak to peak ripple. It's actually a 1 volt peak to peak ripple. It's actually 0.9. A little bit less because what I assumed is that this is 0 time. And it actually, the diode's turned on for a little bit more than 0 time. So the capacitor discharge is a little bit less than I expected. Plus this isn't a straight line. It's got a little bit of bow to it. It's a decaying exponential. So anyway, my design is a little bit conservative. Not too bad though. If I check P2, here's what it is in Circuit Lab. To get the DC signal, what I would do is take the peak, maximum, and minimum, take the average, that's your DC, take the difference, that's your AC. I designed for 100 millivolt peak-to-peak ripple. I actually only got 60 millivolt peak-to-peak. And again, that's because what we're doing is slightly conservative. I assumed that this is a sine wave. I assume this waveform is a nice clean sine wave at 60 hertz. That looks like this. Not a very good sine wave. It's a little bit different. Because of that, my answer is going to be a little bit wrong, but gives you the right ballpark. If you want to fine-tune it, again, I can make the capacitor smaller. Smaller capacitor gives you bigger ripple. So make the capacitor 6/10 of what I calculated, and then I'll get closer to 100 millivolts. Or for this course, call it good enough. Last thing to mention is the difference between half wave and full wave. A full wave rectifier has got 4 diodes. The net result is this is 120 hertz. With a single diode, this will be 60 hertz. What that does is the capacitors are twice as effective. That's 1 over j omega c. The inductor is twice as effective. So I can make the capacitors and inductors only half as big with a full wave rectifier than with a half wave rectifier. So it's kind of your choice. Which is more expensive, extra diodes or bigger capacitors, bigger inductors? So in summary, an AC to DC converter allows you to convert AC to DC. That allows you to drive home appliances with an AC power source. And most power is transmitted at 60 hertz. Most devices are DC, so almost everything that you own has an AC to DC converter in it. The analysis happens in 2 parts. I do the DC analysis, that's the average, and the AC analysis, that's the ripple. And the AC analysis is actually really hard, so what we do is we do an engineering approximation. Here's what the waveform looks like. Let's pretend that's a constant and a sine wave. Let's pretend it's a sine wave with the same DC voltage, same peak-to-peak voltage, same frequency. It's almost the same problem, but now that's easier to solve. This only has 2 terms. It has a DC term and an AC term that's at 60 hertz. When you do that, I'll get an answer that's almost right. If you want to be more accurate, throw it in Circuit Lab. So that's lecture number 8, AC to DC converters.